This is AP Calculus BC, and in this video, I'm going to talk about vector motion in 2 dimensions. So last time we started talking a little bit about vector calculus, and we got into the idea at the very end of taking derivatives of vectors and taking integrals of vectors. So now we're going to just do some simple applications of those ideas. And vector motion is going to work off the same basic ideas that we have done or used with motion problems throughout the year. And so we have the same relationships between position, velocity, and acceleration that we've seen. It's just that now we've got them in this component form, this vector form, or a parametric form, if you want to think of it that way. So the idea is our position vector is going to be written in terms of x and y, or you can think of it as the I and the j components. So then for our velocity, when we take the derivative of the position, we're going to have a velocity in the horizontal direction, a velocity in the vertical direction. And then same thing with acceleration. We'll have it, an acceleration in the horizontal direction and an acceleration in the vertical direction. When we find displacement, we're still going to be integrating velocity just like before. It's just that now our displacement will be in 2 directions. And when we find distance, it's still just integrating the absolute value of the velocity function. Okay, so let's take a look at this example. It says a moving particle starts at an initial position. R0 is at I0, or just I, essentially. It's 1, 0 in a vector component form. And we have this velocity vector. Our initial velocity is I minus j. And the acceleration at any point in time is 4ti plus 6tj. So it says find its velocity and its position at time t. So we saw questions like this earlier in the year with antiderivatives. We did this exact same process. We would start with acceleration, take an antiderivative to get the velocity, and then take an antiderivative again to get the position. So that's all we're going to do here. So here's my acceleration vector. Written in component form, it would just be 4t, 6t. Okay, so to get my velocity vector, I'm going to do the antiderivative here of both components. So that's going to give me 2t squared. Now, don't forget you have a constant here. I'm going to call this constant C1, and then I'm going to have another component. That would be 3t squared plus C2. Notice I'm distinguishing between the 2 arbitrary constants there because the constant that I have for my I component is not necessarily the constant that I have for the j component. So remember, they gave us the fact that the initial velocity is supposed to be I negative j. Okay, so knowing that to be the case, if I plug 0 in for time, I should be getting 1, negative 1 as the resulting vector. So that tells me in the end then that my velocity vector at any point in time, using that initial condition, would be 2t squared plus 1, 3t squared minus 1. Okay, so now we've got our velocity vector. Let's move on and get our position vector. Okay, so for the position, we're going to do the antiderivative again. Now remember, we don't usually use S for position here. We usually use R as sort of our standard position vector when we're dealing with a vector equation like this. So I've got the antiderivative in the x direction, or in the I direction, if you want to think of it that way, 2t cubed over 3 plus t plus some constant I'm going to call d1. And then in the j direction, or the y direction, it would be t cubed minus t plus another constant. Okay, remember here we were given the initial condition that we started at the position I0. So I know if I plug 0 in for time, I should be getting 1 out of the I component, and I should be getting 0 out of the j component. So in the end here, I can write this vector as 2/3 t cubed plus t plus 1, and then the j component will just be t cubed minus t. Okay, now keep in mind, this was just a really simple exercise to kind of see those relationships. Keep in mind, we can have problems where they ask us to find things like find the displacement, find the rate of change, find the total distance. all of those ideas are still the same. You would use, these relationships that we saw above and the same relationships that we've been using throughout the year. Okay, so on this next page, I have an exploration for you on just doing a little bit of work with vector calculus. And what you're given on this problem is a pendulum that is essentially moving in the shape of an ellipse. And you can see that that path is given in the form of parametric equations. So what I want you to do is I want you to try to solve through these problems and work through some of the vector calculus that shows up in order to answer these questions. So what you're going to see in here, for the most part, it's pretty straightforward. But what you're going to see in here are a lot of the types of things that we're going to see in the motion problems that I'm going to ask you to do for homework today. So I want you to try this first, and then I'll show you the solutions. So you can pause the video, take 5 or 10 minutes and work through this. And then when you unpause the video, I'll show you the solutions. Okay, so let's take a look at question number 1. It says the graph above shows the path of a pendulum moving in both the x and y directions. The position in feet at any time is given by these two equations. Find dx dt and dy dt. So all I'm doing is I'm taking the derivative at that particular point in time, and I'm evaluating at 1. You could really do this all on the calculator if you want, but you can see we're moving in the negative x direction and in the positive y direction. Okay, so that's the relationship between the parametric form and the vector form. In the vector form, I would call that negative 2.869i plus 1.672j. But in a parametric form, we can write them out separately like this. Okay, so number 2, it says the derivatives in problem 1 are the velocity in the x and y directions on the figure. Construct these, and then we want to graph the resulting vector with number 3, or for number 3. So you can see I graphed those two, and I can see that my velocity is tangent to the path, that elliptical path that I have there. Okay, so number 4, it says the vector sum in problem 3 is the velocity vector of the pendulum. How fast is the pendulum moving? So we want the speed. So all we're doing is finding the magnitude of that velocity vector at time is equal to 1. So I took those two components that I found on question number 1 and used that as my I and my J component, found the magnitude of about 3.321, and that's feet per second. So that's essentially taking the direction out of this and just saying, how fast are we moving? We're moving at 3.321 feet per second. All right, let's look at number 5. Now they're asking you to look at a second derivative. So we're getting acceleration components. And you can see I took the second derivatives, I plugged 1 in, I got these decimal values, they're both negative. Okay, so now what I want you to notice here is they wanted us to graph these vectors. Notice that we have the acceleration vector and we have our velocity vector. My acceleration vector and my velocity vector are not perfect. This is just kind of a rough sketch. But the idea here is I want to figure out on the next question, am I speeding up or am I slowing down? Now, remember, when we think about speeding up versus slowing down, when we did this where we were just kind of thinking about one dimension, what we would say is our acceleration generally helping that velocity vector get longer, or is it working against that velocity vector and making it shorter? So it appears from my diagram that my acceleration vector is generally sort of working in the same direction as my velocity vector because this angle looks acute. But since I just freehanded that drawing, I need to verify that with some calculations. And we talked last time about how to find the angle between two vectors, and more specifically, how to figure out if it's obtuse, acute, or if it's a perpendicular angle. So in this case, what I did here was I used my acceleration vector and my velocity vector at time 1. I took the dot product and I found that dot product is actually greater than 0. Since that dot product is greater than 0, I know the angle is acute. That means that I'm speeding up. So the idea of speeding up and slowing down still works on the same general premise as what we were doing before, but we have a little bit more information that we have to look at now. We have to calculate that dot product every time we're trying to figure out speeding up versus slowing down. All right, and then one last thing here. They asked you to kind of look at the same thing here in a different way. So what we did was we found a speed function, and then we just took the derivative of the speed function to figure out that, yes, indeed, we are actually speeding up So this is an alternate way you could do it. Ideally, you would just do it with a dot product because there's a lot less calculation involved than trying to create a speed function and then take the derivative of that function. Okay, so you're going to have, for your assignment, you are going to have a worksheet here at the end. And this vector motion worksheet is the only assignment that you have. There's nothing in Wiley Plus because this stuff's not in your textbook. So this is what you're going to have for your homework assignment. Some of these are going to be really simple, and you'll see that they're going to get progressively more difficult as you work through it. But we'll go through some of these in class next time.